Okay, so I am still really sick. Well, relatively speaking, I'm really sick. I still have a fever, and I'm actually headed to the clinic now to go to the doctor. And I was hoping I could pull over and work with you guys, but the timing is such that I needed to be either 30 minutes early for the meeting or an hour late. So I'm just going to make this recording for everybody. Today I'm actually talking about a review of what we've been doing. So I'm just going to go over that. And let me turn my volume up, make sure everybody can hear me. Okay, so we've been talking about Newton's laws of motion, and I just want to review them first. We have the first law, which is the inertia, that things in motion stay in motion, things at rest stay in rest. So with regards to this law, we basically said that things that are at rest, things that are not moving, have a balance of forces. So if you have for example, if you have, say, just anything sitting on a table, okay, that's not moving, the forces of the object, force of gravity pushing it down, and the force of whatever it's laying on pushing back, those forces are balanced. So the net force is zero. And when the net force is zero, then the forces are balanced. When the net force is more than zero, then whatever direction the net force has, that's going to be the direction of the force. For example, let's say you have this right here, and in this you can see that there are 150 newtons of force being pulled by this gentleman here, and 200 newtons of force being pulled by these people over here. So the force is not equal. The net force is 50 because that's the difference between the two forces, and the higher force, or the ones that has the most force, is going to be on this side. So this is an easy example. You could see that this object is going to be pulled this way. Okay, so those are the kind of things that you need to remember when being asked about Newton's laws. The first law is the law of inertia. Things in motion will stay in motion, things at rest will stay in rest unless acted on by an outside force, which just makes sense, but that is the theoretical part of it, because reality, we don't ever have a frictionless environment. There's always friction, so there's always going to be something causing something else to stop. So but this law combines nicely with this law, which is that force is equal to mass times acceleration. The thing to remember with this is you have to remember how to manipulate this formula. So you have to be able to remember to do force is equal to mass times acceleration. But what if I want then to know the acceleration? Well, then it's just an algebra problem, to divide to get acceleration by itself. These cancel out, and then you're left with force divided by mass is equal to the acceleration. And the same is true if you wanted to get mass by itself. You would just divide both sides by the A, and then you would have force divided by A is equal to mass. So you'll need to know how to do that, but this is the second law of motion, that the net force is equal to the mass times the acceleration. Okay, now let me clear that. The third law, which actually isn't on here, says that there's always an equal and opposite reaction. That is Newton's third law, and we saw this when we watched this video here. Which I'm going to fast forward so that you can get a quick review of this video here. And And I can include this link to send you guys.
I remember loving football from day one. I wrote this a long time ago. I don't know how old I was. I hope someday I will be on a...
We're going to fast forward right to here.
Against it. But what does Newton's famous third law really most other forces, it's special because it changes its magnitude. Say you have a piece of aluminium foil stretched tightly across the top of a bowl, and then you put one lonely grape on top of it. Because of gravity, that grape is exerting a little bit of force on the foil, and the normal force pushes right back with the same amount. But then you add another grape, which doubles the force on the foil. In that case, the normal force doubles too. That'll keep happening until eventually you add enough grapes that they break through the foil. That's what happens when the normal force can't match the force pushing against it. But what does Newton's famous third law really mean though? When I push on this desk with my finger right now, I'm applying a force to it, and it's applying an equal force right back on my finger, one that I can actually feel. But if that's true, and it is, then why are we able to move things? How can I pick up this mug? Or how can a reindeer pull a sleigh? Basically, things can move because there's more going on than just the action and reaction forces. For example, when a reindeer pulls on a sleigh, Newton's third law tells us that the sleigh is pulling back on it with an equal force. But the reindeer can still move the sleigh forward because it's standing on the ground. When it takes a step, it's pushing backward on the ground with its foot, and the ground is pushing it forward. Meanwhile, the reindeer is also pulling on the sleigh while the sleigh is pulling right back. But the force from the ground pushing the reindeer forward is stronger than the force from the sleigh pulling it back. So the animal accelerates forward, and so does the sleigh. So one takeaway here is that there would be no...
Okay, so that is something that can be a hard concept to understand. So
without physics. But now we have an idea of some of the forces.
Hold on, sorry about that. I need to go here. Exit full screen.
We might encounter.
Well, now I can't figure out how to exit full screen. Okay, there it goes. Okay, so let's do a couple of practice problems with this. That's the law of thermodynamics. Let's go up to this. So here's a practice problem. This is in Study Island. And at this point in Study Island, you guys should basically have all of life science, all of earth science, and the only two blue ribbons that you should not have earned yet is the wave characteristics, which we're going to start next week. So everything in Study Island should be done except for these two right here. Okay, let's look at these. The question is the chart below summarizes the force applied to different objects. Which objects will experience a greater acceleration? This is just that math problem I showed you, where you have force over mass is equal to acceleration. So then you just have to get out your handy dandy calculator and you have to calculate to this over this and see which one is greatest. That's easy enough to do. So let's move on to the question 2. Newton's blank law of motion states that for every action there is an equal and opposite reaction. Okay, that's the third law. All right, so let's keep going and do a couple of more. A book is sitting at rest. Which of the following best describes the forces acting on the book? Okay, so let's look at the answer choices. The force of the book are balanced forces because the gravity pushing up on the book is equal to the friction from the table pushing the book to the right. Okay, this would be right with a couple of exceptions. The forces on the book are balanced. You know it's balanced because the book's not moving, it's at rest. When something is at rest, it's balanced. But here's the thing, is The gravity pushing up. Well, gravity doesn't push up. Gravity pushes down. Okay, and then it says the friction from the table pushing the book to the right. Okay, that doesn't make sense. When you have a balanced force, they're going to equal each other out. They're going to look like this. No matter what the scenario, the forces that are in motion are going to look like this, where they're balanced, where they're equaling out. That's not a great drawing, but you understand what I'm saying. So let's move on. The forces on the book are unbalanced. Nope, that's not right. We know they're balanced because the book's not moving. The forces on the book unbalanced. Nope, that's not right. I already know the only possible correct answer for this one. Oops. I already know the only possible correct answer for this one is D, because I know A is not right and I know B and C are not right. But let's just look. Gravity pulling down on the book, okay, got that, is equal to the upward force applied by the table. Again, that's what it's supposed to look like when they're balanced, and that is exactly right. Okay, so let's move on to 4, and then we're gonna, oops, go back. Okay, 3 dogs, Egg, Max, and Marcy, are pulling a dog sled along a patch of ice. Ed pulls with the force of 115 newtons. Max pulls with the force of 62 newtons. Marcy pulls with the force of 90 newtons. By the way, newtons is the unit measurement for force. Kilograms per second squared is the units for acceleration, and mass, the units are usually grams or milligrams. So if there are no forces pulling on the sled backwards, what is the net force acting on the sled? Okay, so you have a dog sled that's moving. So you know it's not an unbalanced force. So you know it's not going to be 0, okay? Because there is actual moving. And you know it's moving forward, which all of the answers are forward. So now you have to figure out what the answer is. Okay, so here's how to answer this question. This is a hard question. You have 90 here, 62 here, and 115 here. Okay. So here is how you are going to answer that question. You have to think about, give me 1 second. Oops. Okay. You have, first of all, let's add these up. 90, 62, and 115. Yikes. Okay. Get my calculator. That, not my calendar, but my actual calculator. Now I'm going to say 90 plus 62 plus 115. That's 267 newtons. Okay. This is why this is the answer, because it says if there are no forces pulling back. In a typical, in a real life scenario, this is not possible, okay? But it says there's no forces pulling back. So then you just add those forces together, and that's 267. All right, let's move on, oops, to the next one. Which explanation describes the forces involved for a person to walk down the sidewalk? Okay, well, let's look at the options. A, the person's feet push forward on the sidewalk pushes forward on the person. Okay, well, a sidewalk isn't going to push forward. Remember, you just draw the picture if you're not sure. Just draw it. you have a person on a sidewalk. It says the person's feet push forward. Okay, so actually, if I was going to draw forward, I'd probably draw it like that. Yay, this is a really weird looking person, but okay. And then it says the sidewalk pushes forward. So then the sidewalk, they're walking and pushes forward. So that doesn't explain it. So that's not it. The person's feet push backward on the sidewalk. Okay, so you could even maybe draw that looking like that. And the sidewalk pushes back on the person. Okay. Well, that looks right, but let me draw it a different way. It would actually be more like this. The person's feet push backward on the sidewalk. So it would be like this. And it would be like this. The person's feet push backward on the sidewalk. I'm assuming the person is walking in that direction. And the sidewalk pushes back. So that doesn't make sense. The first person's feet push backward on the sidewalk pushes forward on the person. So again, you have backward and forward. Here, you have backward and backward. Here you have forward and forward. So this one is correct because even though, however you draw it, you have forwards and backwards. This one, you have forward, and then you have no push. So the only possible answer is C because you have a backward and a forward. So again, this is Newton's third law. For every action, there's an equal and opposite reaction. Okay, so that is a review, but what I want you to do is I want you to go to IXL, which I thought I had already pulled up. Yes, I did. Here it is. Okay, I want you to go to IXL and I want you to do some practice problems. Go to Oklahoma Standards, go to 8th grade, go to Science, and you're gonna go where it is right here. These right here. Identify whether objects are accelerating. Remember, if something is accelerating, if something can be accelerating, in order for acceleration to happen, you have to have a change in motion. Okay, but practice these. I'm actually going to submit those in the email that I send you. And you guys, I apologize for the inconvenience of not being able to meet with you. And again, I've literally had a fever for a week. As of Saturday, it'll be a week. Today's Friday. So tomorrow I would have had a fever for a week. And so I'm just going to go ahead and go to the doctor. I had a meeting that I couldn't avoid this morning. And so I'm literally sitting in the car about to head into the doctor's office. So I appreciate all of y'all's support. And please take the time to, ask me any questions and do those IXL practice. Okay, you guys, I hope to see you soon.